Excellent. So welcome, guys. Thanks for being here and nice and early. Get started. So final presentation. All right, and we should be live on air as well. No guests have joined us yet, but I'm sure people will join along. Okay. So the order of presentations are up there. Okay. So we'll again, as usual, 15 minutes, ideally 12 minutes. Justin over there is keeping time, and he'll tell you when there's 5 minutes to go, 1 minute to go. We'll take questions, okay? But we'll keep it brief. We'll take a break at 10:45 or maybe 10:50, depending on how we go with time, okay? Quick 10-minute break before we come back in. And if you have more questions, we can ask during that time, okay? But pay attention to Justin as well as he keeps time as we go along, because we want to try and keep time, okay? So we'll start with team number 9. All right, I'll let you guys introduce yourselves and the game.
Hi, we're Team 9, and we're going to be showing off our Capture the Flag game.
So, a quick reminder about what was the first assignment about, because we built on it. So, what we had is, how am I supposed to play it from here? No, let's play. Is it? Okay, cool. What we had was a capture the flag game with a player that you could control to capture the flag and return it around here. So there are enemies AI with finished state machines that could do basic actions like attack your player, run to an alarm, flee, and so on. So we had finished state machines, we had pathfinding, and we also had steering behaviors. We changed the game quite a bit to make it two-base capture the flag. So we now have 2 teams, 2 AI teams, and 2 flags and 2 bases. What we are trying to do is, we'll have 1 team with reinforcement learning and 1 without, 1 with the simple behaviors showed before. So yeah, this is what it looks like.
So this here is actually just a close-up, zoomed-in version, just so you can see each player attacking each other, 2 teams fighting against each other. So there's no player anymore, it's all NPCs. In the top left corner is the neural network being used by the current selected guy who just died. And we'll go into more detail about that in the next coming slides.
Yeah. So our goal was to build an environment for NPC to play Capture the Flag, like I said before. And we implemented reinforcement learning using neural networks. So we wanted to evaluate both AI techniques and see which one was the best. Yeah. Good.
Cool. So I'm just going to run you through basically behind the scenes how it works. We started off with a very simple state machine. Basically, we've got attacking, capturing, and defending, the 3 decisions that each NPC can make. Attacking basically just means shooting the closest person to you or running to find them and then shooting them. Capturing involves running towards the enemy's flag, picking it up, and then once you're holding it, returning it to your base. And defending means hang around your base and attacking whoever is closest to your flag and returning it if it's missing from your base. So the way we wanted to do it was have a neural network that is checked on every single update to make a decision of which of those 3 behaviors it should be doing. So to give you a quick foundation of a neural network for those who aren't aware, this is somewhat what a neural network looks like. We've got our inputs on the left-hand side. Basically, it runs through a series of mathematical operations, and you get an output at the end, which will tell it which of those behaviors it wants to do. So to quickly run through it, we can see that each of our inputs, we might have things like, for example, we had the player's health, how close it is to the flag, how many enemies are around it, basically like a threat level. Each of those inputs are multiplied by a weighting, which is calculated by the neural network. It goes through this function, which is run in every single node. Here's what is happening here is we've got each of our weights added together from each of the inputs, and then it goes through a non-linear function, which is this f of e. The purpose of this is to basically get all the inputs and put this number in between a range. We had in between -1 and 1 because our function was hyperbolic tan. And this basically means that because it's nonlinear, it's going to push those results towards -1 and 1 and have less results than 0, so less ambiguous results. Once you've calculated up each of these nodes, you'll get to the end and you'll calculate an output. You'll then compare that with a desired output of what you were hoping to get out of the neural network, and you'll calculate the error. You then calculate the error for each of the nodes within the network by timesing the error by the weights that lead it into it. And once you've done that for each of this, you then get your new weights. This is using backpropagation. You get your new weights by adding on the, got my pointer, times the learning rate, which is just a constant factor, by the error of that weight, times by the derivative of our nonlinear function. So in our case, we had hyperbolic tan, and the derivative, of course, is sec squared x. And we multiply that by the input. And once you've done that for each of the nodes, then each of the weights will be adjusted. And on each time you run it, the weights will be more adjusted to produce the right output. So here's our design for our inputs. We had, is your flag currently captured? Whether or not their flag is captured, these sort of simple inputs that we can put in. How many enemies is nearby? It's basically a range of basically a threat level. So if there's a lot of enemies nearby, then it's going to be a high threat. For example, if it has low health, we might want it to run away as opposed to standing and to keep fighting. And the outputs, yeah, the 3 behaviors that we said before.
So in addition to our backpropagation neural network that we use for our initial, we get the weights, our initial weights of our backpropagation neural network by having training data and initial data, testing data, and these are created from policies, which we created as a base level for them to have some behaviors when they first start, because otherwise they swap around quite randomly and don't really know what to do. So we had some attacking, defending, and capturing policies between different ranges that we manually created, and then we test them against and we use them to test against our initial data when we're running the backpropagation. This is a video of them in action from like a high-up perspective of them actually playing the game. Up in the corner here, we have our neural network. And so this would be our initial neural network that was created by the backpropagation before the game run. But then we have reinforcement learning in the game, and that will then modify it in-game and save that for later. And that's how they can learn behaviors, and that's not just from our initial policies. And we also have we keep a score and stuff just so that we can have some data, of which one's doing the best, as we planned originally on having a genetic algorithm. So our reinforcement learning we have rewards and punishments, and that's how we reinforce the weights. And if it gets punished, it reinforces everything except what it just did by going back. We have, so the punishments are things like getting shot, getting killed, your flag getting captured, etc. Rewards are also shooting the enemy, capturing their flag, etc. And we can have different levels of punishments and rewards. So capturing the flag rewards you a lot more than just shooting someone. So as we said before, we save and load our data in files, and this means that we can run the game many times. We don't have to run it in one long session, which I know other groups did and could be annoying. It means we can run it over like multiple smaller sessions as it keeps the data persistent of the weights. And we have respawns in the game to make it so the game is just a continuous, never-ending. As otherwise, you just have to restart the game again and again. And like I said before, we have our leaderboards, which allows us to keep track of the kills and deaths of all the players, as well as if they get any captures.
All right, so in the end, our neural network was successful with a 91% accuracy. We still need to improve our rewards and punishment a little bit in two ways. The first one is that we need to tweak a little bit the values at which it modifies the neural network to make it more accurate. And the other thing we'd like to do is, currently on our rewards and punishments acts only on the last action of a player. We'd like it to act on a series of actions, because it's not probably because of the last action that something went bad. We also would like to implement genetic programming. So what we want to do is, from time to time, just erase the worst AIs and replace them with a combination of the two best plus a mutation. So yeah, that's pretty much it.
Yeah. Also, yeah, just with our current policies, things like the capturing isn't quite. They basically never try to capture the flag because they get rewarded too much for just shooting enemies. So this is definitely shows us how important it is to tweak our rewards and punishments.
Yep.
As at the moment it's more a massive shootout than but they do learn a bit better about when to defend and attack and stuff. How much time do we have?
That's it.
Just about done.
Okay.
Yep. Brilliant. Thanks everyone. If you've got any questions, you can now ask them.
Questions?
Yes.
Any?
Just a quick one. When you started, because you're doing reinforcement learning, right?
Yeah.
And I'm not too familiar with the neural network side, but when you start the game off, do they know anything? Do they assume something?
Yes, so we pre-create a base neural network using the backpropagation methods. That's all done beforehand with our initial policies that we created. And so they use that as their base, and then that's modified in game.
So just to explain those initial policies, basically we had a set of assumptions that said, basically if you're really close to the enemy's flag, well then we want it to run and pick it up. If you're surrounded by a lot of enemies and you've got to let off health, then maybe you want to attack them. If you're nearby to your flag and someone's just picked it up, well then maybe we want them to decide to defend it and return the flag. So basically we came up with a set of initial policies, as we call them, which basically just means a set of inputs where we have a desired output. We created a set of training data by, we had a set of ranges for each of the inputs next to our set output, and then we just randomized training data in between each of those ranges. And then we trained the game before we ran it using those initial policies. And then once it's running, the reinforcement learning should improve those policies better than the initial policies we first created.
Yeah, as our initial policies, to some extent, are guesses of what behaviour we want. So yeah, it's always doesn't work perfectly when put it in.
All right, good. Let's thank Team Learn again. Next team is 3. Does anybody when you're ready? Ready to go? Okay, right. So Michael and Jaden, off you go.
Awesome. Okay, so today we'll be presenting the game we made for assignment 2, where we use genetic algorithms and neural networks, and we'll just jump straight in with the video. So this is just going to be a video of the gameplay. So the player selects the group of flies, and their objective is to look for resource trees which are placed around the edges of the map, and once they get the resources, to then bring it back to the base, which was that tree in the middle. The frog's using a neural network which was evolved with a genetic algorithm, and the trees are also placed around the edges of the map with a genetic algorithm. So we'll see here soon that, yep, they've got some resources now, so they're going back to the base to actually return those resources and score some points. We've also limited the player's vision, so they're not really sure where those trees are on the map or where the frog's going to be. So you'll see here now the frog comes in, he's trying to eat the flies. We also have these snakes around the map which are just autonomous, and they act to scare the frog away so the player can use them to their advantage. And as you can see there, the frog just used his bubble to trap the snake so he could then successfully chase the flies. So we'll give a brief overview of genetic algorithms because we didn't cover in the course material, and it'll kind of help to explain what we did. And we'll do this using that example of placing the trees around the edges of the maps to kind of put it in a less abstract context. So the basic idea of genetic algorithms is that they're modelled after the theory of Darwinism, whereby the fittest individuals in the population survive and return in the next population. In our example, here we start off with some initial population where that's just a chromosome, and that chromosome is the list of different positions on the map which we can place the trees. And each gene in that chromosome is each individual position. We apply our fitness function, which evaluates each of these chromosomes and assigns some value to it to say how good it actually is. Then we perform this selection method here, where we grab two parents. Usually it's the ones with the higher values, but sometimes you do want parents which don't have a higher value just to kind of keep it a bit random. And then you apply this crossover operator where you breed the two parents getting some characteristics or genes from both of them. So for example, we could split the list of positions in half, take half from one parent and half of from the other. And then we perform this mutation operator, which in our case was just going through each of those genes for the positions and just saying, okay, move this position up a little bit or down or just somewhere else on the map. And this is some of the results we got. So here's one of the maps on the left. Got these trees over here and there, and then over here we've got a different set around the edges. The middle always stays the same. So what we're trying to do was to encourage the player to explore the map because it's dark and they can't see what's going on. And this way they don't know which side has more resources. So in this case, it's more beneficial for them to go here because they'll be able to collect resources much faster than it is to go over here where there's only one tree and it's going to be much slower.
Okay. For those of you who are watching online and don't know who I am, I'm Michael, and my job in this presentation is to explain, just stand over here, neuroevolution. I'm glad the previous group explained what neural nets do because I wasn't really planning on doing that. The basic idea of neuroevolution is, it is kind of what it sounds like. It's evolution applied to neural networks. So the idea is that if you look at a neural network like these and you read off the weights from the top to the bottom like this, then you can treat the weights as an array, and then you can apply the genetic algorithm techniques that Jaden was talking about, chopping the array in half and crossing it over or mutating individual weights. So yeah, I just wanted to highlight though, there's one extra thing with neural networks that you don't normally have to consider with a general genetic algorithm, which is with the crossover operation, you don't want to just chop the array at any old point. The thing is, after the learning algorithm has been going for a while, it's likely that the weights going into an individual neuron will be highly tuned in relation to each other, so they'll be in some sort of ratio. And if you just chop the array at any old point, it's likely that it'll chop in between a neuron's weights. And when you cross over, you'll kind of mess up that fine-tunedness, and the child is probably going to come out pretty dumb. Oops. Okay, so this shows sort of the level of complexity of the neural net that we ended up with in the game. So this is literally it. We had 13 inputs along the top. So it was the nearest two flies, the nearest two snakes, the nearest two obstacles, and the nearest two lakes, and also the frog's current water level. Now all of the inputs, so a nearest fly, that's two inputs because it's the X position and the Y position. And it goes through the mysterious hidden layer, and then it comes out the bottom with the XY steering of the frog. Now, there's another complication here with the inputs, which is you don't just want to feed in a vector from the frog to, say, the fly or to the snake. Because if you do that, the magnitude of the vector to the fly, for instance, will be much larger if the fly is a long way away, which isn't really sort of what a human sees. the fly gets close to a human, you see it become big, and if it goes further away, it's like the fly's not even there at a certain point. So we transform the input so that when a fly or a snake is right on the player, it comes through with a magnitude of 1. And then there's like an exponential decay curve that decays it down to 0 as the fly or the snake gets further away. Yeah, and we were slightly concerned that with a network of this complexity that the genetic algorithm wouldn't really be able to learn very much. We'd sort of read in our book that you generally want maybe 3 or 4 inputs and like a few hidden neurons and 2 outputs, otherwise it's going to take for ages to learn. But we found that this was actually quite effective as is. So I've got a quick video to show you. Oops. I'll have to run this off the Alt tab. This is showing a training pen that we set up to train the frogs, which isn't the actual game, but it shows, I'll just let it play and then I'll talk about it actually.
Do you want to go full screen?
No, then you'll get a lot bigger. Okay, so this is epoch 1 when the weights are randomized at the start. And the frog has basically an equal chance of doing anything. Here it's just ramming a snake really stupidly. So it gets really low fitness. Now, by the sort of middle stage of training, it's learned to protect itself, but it's learned to protect itself by just jumping into a lake. So it's not particularly interesting. It just sits there for like 20 seconds and, well, it gets a lot more points than the first snake, but it's not particularly desirable behavior. Okay, and now in this later example, you'll see, oh, uh-oh, can't see the full thing. Can we just go back a bit on that?
Yeah.
Okay, so again, this is why we were running off the laptop.
That's okay, that's fine.
This will be a shame. This is the coolest one by far.
Good go.
Okay, so by the end,
Oh no.
it's learned to protect itself by going in the lake. Then it pops out and does some cool stuff. Sorry, that was a bit disjoint, but basically it jumped into the lake at the start. It chilled there for a while until it realised that it was safe to come out because the snakes were sort of close to it. Waited till they got a little bit further away. Came out with its water level being high. It was able to bubble the snake, push the snake out of the way, and get a fly that was underneath. So the behaviour that emerged was actually pretty cool. I mean, we saw from the video that it looks like the frog is learning and it's become a lot smarter, but I guess normally in a scientific setting you want to quantify that somehow. So what these graphs show is, this is for the trees learning, this is for the frogs learning. It's the total population fitness as the epoch increases. So notice for the tree it's pretty steady, there's a steep learning curve at the start, then it just gets a little bit better as it goes. With the frogs, the learning's a bit more jagged because the positions of the flies in each of the training runs are randomised. So if the flies are in a really favourable position, it's likely that that population will get a really strong fitness, whereas if the flies are sort of placed really close to the snake starting positions, then it's going to be less. It doesn't actually matter because within each epoch, the strongest frogs will still be selected, but it just means that the output line is a bit more jagged. You can still see the trend up. So that is it. I skipped over a bit probably with the frog learning, so if there's any questions. Yeah. Is that?
What's your method on like selecting the 2 best parents?
Okay, so we tried a few. Originally we tried some really basic techniques, which is proportional selection, where basically you take the fitness of all the frogs and their fitness determines their slice of the pie, their chance of being chosen as a parent. But we found that depending on the fitness function, sometimes you would end up with the fittest frog getting like 70% of the pie. It depends where sort of the 0 scale is for the fitness function and things like this. And it was leading to like not enough genetic diversity in the gene pool. So what we ultimately used was rank roulette, where all the frogs are ranked from 1 through to, I think it was 40 here. There were 40 frogs in the entire pool. And the top one gets a bit more of the pie, but it doesn't get like drastically more. It might be, say, sort of like 1.5, whereas the bottom frog in the entire population might be, say, 0.4. So, you know, a 3 or 4 times chance being selected over the worst one.
Yeah. Can you go a little bit more into what you use for fitness function?
Okay, so yeah, sure. Originally we used basically just flies caught minus, I think, 7 times the damage from a snake, so it's prepared to catch flies. You know, it's happy to catch 7 flies, or it's neutral if it catches 7 flies and then it gets hit by a snake. It was a little bit tricky though for the water camping thing though, as you saw in the Epoch 250, because what happened was once the entire population learned to just run into the water, no more learning really takes place at that point, because the ones that venture out tend to get hit by snakes and they're worse off. So we actually ended up adding a water camping factor. So once they're full on water, because we did want them to be able to fill up on water, once they're full, it starts detracting points. There's a little bit of a grace period so that it doesn't hurt frogs that stay just, you know, a second too long. But you see that what happened is if I'd shown you like Epoch 600, they'd sort of run to the lake, then they'd sort of circle out and circle back in, and circle out and circle back in. But it was enough that they would eventually realise, oh, there's a fly here, and the behaviour could evolve to the next stage. One thing I also didn't show is there's actually 8 training pens all side by side, so that we could train the frogs a lot faster, and we used the Unity speed up factor, obviously, to increase the learning speed.
Good. Live audience, any questions? No? All right, we're just happy watching. All right, thanks, Michael, and again. Let's go on to team 8.
Hello everyone, so this is Matthew, this is Mewen, and I'm Lucas, and we will present you our game. Small summary of our presentation. First, we'll introduce the game and what we had to do for this assignment. Secondarily, we will review a bit the project and see what happened. Then we will talk about machine learning, and then you will be able to ask questions.
Thanks. So, for this course, we have been able to create a game, and in this game we have implemented several concepts that we learned about artificial intelligence. So, our game is about an overlord that we try to save his minions that are located randomly in a map, and on his way to achieve his goal, he will find some enemies that are the good guys that will try to avoid this to happen. So what we're going to present today is the extension of our first assignment. And so what we've done more is some fixes about the first one that was more about pathfinding, obstacle avoidance. And then we implemented a new feature in this assignment, that is the machine learning. So to make our prey and predators more intelligent and provide an experience for the player, a better one. So here's a small video of what we've done. So that's a review of all the features that we got. So among the steering behaviors, you get some flee. That's you got the good guys at the top and the prey fleeing. We got the flocking, so you got the overlord and all his prey are flocking around him. Then you got healer. And the pursue behavior, so you can see the good guys that are trying to get the predator and some obstacle avoidance. Yeah, it's pretty dark, we don't really see. So that was all about our first assignment, and so now we will present you the machine learning that we've implemented.
So we chose to use decision trees for our machine learning because we thought that it was what would fit the best our game. I will firstly talk about the algorithm. So we used C4.5. It's an algorithm based on information entropy, which is the average amount of information you get from each attribute. So what the algorithm does basically is, firstly, it retrieves the information we stored. Then for each attribute, we find the highest information gain. Oh, no, sorry. For each attribute, you split the tree on it to find the information gain. Then we find the attribute that has the highest information gain. And then you build the tree with it. So we choose this algorithm because it provided a few different features important to us. Firstly, it could be pruned or unpruned. The pruning, is when you forgot a bit of data which is not important to the tree, and it allows to reduce overfitting. So, well, that was not that important to us finally, because we didn't have that much different attributes, so it didn't really overfit it. The algorithm also handles missing information, which is important because sometimes we didn't have information for an attribute. And then it could handle different data types. So it could be integers or floating points or characters or whatever we wanted. Then it could be online or offline learning. We choose online learning because it provided a better experience for the user, because our game is pretty much different it's always different depending on how the player play. So online learning will learn depending on the player and not on our tests. So now I need to Matthew.
So I'm going to talk about how it was implemented. For our assignment, we used Weka, which is the Waikato Environment for Knowledge Analysis, and that's from the Waikato University in New Zealand. The Weka library is just a set of, or a whole group of machine learning algorithms that is written in Java. I believe it's open source, and I've used it in the past, so I knew that it would work for what we needed it for. So using Weka, we wrote a library in Java, just consists of a single class that has a whole bunch of hard-coded methods, hard-coded values specific to prey and to predators, because that's where we're applying machine learning. The methods allow you to teach the trees and to request decisions from them. You can also actively tell a tree to be rebuilt if it hasn't been rebuilt for a while and you want it to rebuild at a specific point. Having written the library, so that we could use it in the C# environment, we needed to export it to a jar, including the Weka library, and then convert it to a DLL using ikvm.net, which is something that is included in C# installs. So now I'm going to talk about how they're applied to the prey and the predators. Both types of agents have different information that would be useful for them in their learning environments, and how they would learn would differ as well. So first up is predators. In the predators, there were 11 features for their vector, or their feature vector. If it has an N next to it, it's a numerical value. If it has a C next to it, it's a class value. In the case of Weka, a class is just a set of different possible strings, I suppose. So predators cared about health, distance to safety, distance to player, the nearest flock, other nearby predators, targets that were in range, flock size, player health, nearest prey health, current state, and the decision that you want from the tree always has to be included. You can put it anywhere that you want, but it's usually good to have it at the end. For predators, based on the previous finite state machines that we used, current states were idle, pursuing, or attacking, and they could decide to attack the player, attack the nearest member of the flock, or just simply idle. Now initially when we were doing this, I tried to build some basic training data that I thought would provide some behaviors that would make sense. when testing that, it didn't seem to make much sense. So I scrapped the idea of initial training data, and we added in some encouragement against illogical or really just dumb behavior. So the main one of this was if they request a decision and they're already idle and the decision says to remain idle, the logical thing is a decision is requested every time a state changes, and a state is changed based on a player coming nearby or leaving, or a member of the flock entering or leaving range. And so remaining idle is dumb. So we trained it so that if it was told to remain idle, it would learn the other things instead and then re-request a decision in the next frame. It would also learn when it successfully landed a strike by delay after a decision or by distance during a pursuit. For the prey, they had 7 features in their vector. There was health, distance, safety, player, nearby predators, flock size, current state, and decision. Current states were idle, fleeing, flocking, attacking, rescue, and dead. And decisions were flee, follow, attack, and idle. Now the attacking and attack are there because we had initially thought to make it so they could attack, which would make some interesting behaviors, but we didn't end up having time to implement it. So anytime it was told to attack, it would instead idle. These were again encouraged against remaining idle, but they would also learn after a decision. If they were rescued, the most recent decision was a good one, so they would learn that. And if they died, they would learn every other decision other than the previous one that they made. And next, results. Okay, I'm talking about results as well, it seems. So this is the results over 50 runs of each no learning, predator learning, prey learning, and both of them learning. For the first 100, where there is no prey learning, that arose because when the player entered range of a prey that hadn't learnt anything, they, for some reason, decided that fleeing was good. But when there's nothing to flee from, they just stand there. So they never leave their spot when the player enters range, and they never get taken back to the safety. So they don't learn. The predators also don't kill them, which is the orange lines, because, again, they never leave their little safe spot. They just kind of stand there looking stupid. In the next one, when prey are learning, allies rescued, we have not quite a, well, definitely not a linear progression, but this doesn't take into account when the player dies. So the player was capable of being killed just as much as the allies were, and as soon as the player dies, that run ends. And so that's where the discrepancy between some being saved and not being saved comes from. And it was also possible that when a player went to a point on the map, they wouldn't pick up all of the allies in that location, so some would just continue wandering around whistling Dixie. The last one here is when they're both learning. So the predators, when not learning, would try and attack the player at all times. But when they were told to learn as well, they did seem to have a strong desire to kill the prey as well. Again, there were situations in here when the player died too, and so that's where the not 15 in total comes from. And that's it. Are there any questions?
Any questions, guys?
Any questions from the members of Google Hangout? Okay, thank you very much.
All right, thank you. All right, next group ready?
Hi, we are Peter, Tristan, and my name is Franziska. Today we will present you our game Save My Job, where Wabush has a life and is able to walk and wander around. A janitor has to collect all pieces of rubbish and bring them into a recycling area, while Wimbers, smart cleaning robots, are trying to eat them before. Therefore, the janitor has to be very fast and to get a higher score and to save his job. Currently you can see our game running, and the text boxes are explaining a little bit what happened there. Maybe you have seen some lines on the ground. They are showing our previous task in terms of pathfinding, whereas the changing colors showing the different states of the finite state machine and the steering behaviors. At the beginning, yeah, you have maybe seen that there was only one Roomba, but in further levels we will have up to 4 Roombas, and every of these Roombas is implemented with its own personality, which is really close to the personalities of the Pac-Man ghosts. But today we want to speak about our 2 franchise approaches to make the Wabbush smarter and more resistant. We have on the one hand the evolution and on the other hand the aftermath. While the evolution uses an online approach to where the Wabbush can learn with every gameplay, the aftermath uses an offline evaluation of different features where to reach the same aim. My peers will now talk about both approaches in more detail, and they will follow the listed points on the slide.
Thanks, Francie. Okay, I'm Peter, and I'll talk about evolution. So, first question is, why would you bother to use a genetic algorithm? For us, it was kind of irresistible. Our trash had crept out of the primeval slime, so it was very tempting to see what would happen to it next. In terms of using a genetic algorithm for a game, the only real reason to do it is to improve the gameplay. So that comes down to 3 things. So we want to increase the replayability, which typically means making it less predictable. We want to increase our enjoyment, which usually means making it more challenging, but research shows that it doesn't want to be too challenging, because we don't like that. And we also like to have realistic non-player characters, which can be a bit of a challenge with trash, but I'll come back to that. So, going from the finite state machine to the genetic algorithm. The finite state machine, everything is controlled, obviously, and very, very predictable. So what we did was to take every single trigger, every constant, every weight for the steering behaviours, anything that could influence the trash's behaviour, and parameterise it, and then encapsulate each one of those attributes into a gene, which would then have, instead of being a constant value, was like a range of possible values. And then when the trash is generated, which happens at the beginning of each level, when the trash is generated, then its values of the genes are fixed. So the trash actually behaves, its behaviour is consistent within itself, but when you're playing the game, every single piece of trash actually behaves differently depending on its chromosome. Somebody's already described how a genetic algorithm works. I didn't want to go into detail anyway, but the key things here, and the things that are different and that influence the challenge and unpredictability of the game, first of all, it's applied absolutely literally. We're not trying to get the best possible trash. And the fitness function is purely based on survival. The trash that lasts the longest scores the highest. But this is the thing that's unusual, is that instead of discarding the worst performing trash and evolving the best performing trash, we keep the worst performing trash and evolve, mate and mutate the best. So then you get some trash which is harder to catch, but you don't make the game too hard, so you don't want to play it. And so it turns out that a genetic algorithm is kind of win-win from a gameplay point of view, because if the algorithm works really well, then you get a challenge, but if it doesn't work that well, you still get a different set of trash every time. This is a quick demo. Everything happens on level 4 in evolution. There's no furniture, there's no Roombas, because what we're trying to do here is to make sure that the trash evolves completely in response to the player. So if it was a more complex game with a different player, you'd expect the trash might evolve quite differently. Here, all we're really seeing is that everything is responding at different rates. So it's got a different reaction distances, different speeds, different acceleration, everything, and fleeing at different angles. All that stuff is different for different individuals in each generation. And when the score comes up, the generation is captured alongside its score, when it actually was captured, and that's like a later iteration. So what we found was, yeah, it did tend to. Let's try that again. There's a tendency that the more evolved trash lasts longer. This slide is really just about potential. It talks about making non-player characters more believable. The genetic algorithm is very simple. It's relatively successful in doing the unpredictability thing and the challenge thing. In this implementation, every single aspect of the trash was treated individually. So each gene encapsulated absolutely one separate quality. But what we could have done was to group qualities like, the flee speed or the reaction distance from the predator, group those things together into wider traits like courage or other things into curiosity or sociability, and then apply exactly the same genetic algorithm, but then we'd be evolving based on personality instead of just performance. So that could be quite interesting. And the other thing that we could have done with the genetic algorithm would be to develop uber trash. Genuinely uber trash, but that's something that I'll let Tristan talk about.
Yeah. So I'll be talking about our other method that we use, which the game's called Aftermath. We made a significant game redesign. We removed the janitor, so it was now just trash versus the Roombas. Our intention was to make better trash. This means better survivability and to avoid being eaten. Originally, we aimed to build a decision tree, but moved toward a type of reinforcement learning, as you'll see from our results. We wanted the trash to learn when it's best to flee the Roomba and when it's best to get recycled. Here are the features we deemed important when making that decision. So the distance to the recycling area, the angle between the Roomba and the recycling area, the number of members in the flock, and the charge level of the Roomba. We aim to test different value ranges for these features and analyse the results. The ultimate goal was to have a game iterate, so the subset of ranges for each feature, through a subset of ranges for each feature until an optimal solution was found, therefore having the best trash. So here's a demo showing the automatic gameplay that we set up and the testing of the initial features. So the game obviously plays itself. We've got just kind of a debug showing the settings. Here, the features that we're testing are just the recycling distance and the Roomba angle. You can see when the debug line comes up, that's when they're deciding to actually flee towards the recycling area. And of course, when they're close, they do so. And that's the iteration. You can see the run counts as well. Through our testing, we only did about 10 runs per set of features, and ideally would have done a bit more. The score data from these runs was saved to a CSV file for offline analysis. Okay, so the first set of results that we got weren't that great, and we realised that we had to improve our scoring system. The second run through after improving the scoring system, as you can see the original and the revised one, we got data closer to what we were hoping for, but it's not enough to implement an automatic analysis in-game, so it was still offline. We did get close to achieving our goal, but the process was not as straightforward as we thought. This could be extended with additional features. With additional feature testing, it's possible for the trash to automatically trend towards the optimal features, but our results indicate that this requires a much better scoring function, or at the start, figuring out the scoring function. And we'll just have a quick comparison between Aftermath and Evolution.
Oh yeah, just to say, Evolution obviously was online, and you saw these results immediately, whereas Aftermath offline and had to be analysed. They both actually depend on the evaluation scores, but Evolution is unique to the particular player. And while the main difference, though, is that Aftermath is trying to evolve the best possible trash whereas evolution is just about the gameplay. And that's it.
That's it. Any questions?
What was the fitness you used for the evolution side?
The question is, what was the fitness used on the evolution side?
It was absolutely literal. The trash that lasted the longest scored the highest, and the trash that didn't last long scored the least, and it was just run by run. So if there were 10 trash items, the trash that lasted longest scored 10.
Okay, so we've got some
Couldn't have been
live
simpler.
viewers. Tristan, you have an awesome beard, so that's good. And the other question is, in terms of using path planning, did you, I guess the summon wasn't really about path planning, but someone's interested in if you use any path planning, any variations of A* is the question. Did you use it?
We did it in the original implementation. We did use A*, and we also used a greedy algorithm just to select first step. So sometimes we wanted the trash just to move one step, and so we just used a greedy algorithm for that.
Cool. Any other quick questions? Yes.
When you try to get the how did you select the
best items of trash?
And the best trash, and then mutate it?
Well, I sort of split the trash in half. So the worst ones were kept absolutely as they were, and the top 4, literally the first 2 I combined, second 2 I combined, and I did swaps, although they were, it wasn't like a binary thing, but I still just did direct swaps with all their values. Could have merged them, could have done like an average. Didn't do that. I just swapped them, and then I just did. There was a number of mutations, so just went all the way through the chromosome, and chose a new random value, because at the first level they're all random. So it was easy to just say, okay, now just give me a random value for this particular gene.
All right. Well done.
Welcome everyone. Our game is called Save the Plebs. We'll go into details of what we had for the last assignment, but we're Group 7 and I'm Andrew, this is Jeremy, and Shuj on the end. So for the presentation we'll just be going a quick overview of the game as a game, and then we'll go into the machine learning aspect, and finally a bit of reflection on how everything went and what we could do better.
Cool. So basically, our game involves you as a player. You lead a bunch of villagers through a dungeon, try not to get killed by the bad guys, and get them to the end. There's a fairly big view because it's a top-down camera. Yeah, avoid the monsters and guide the guys to safety. It's just a bit of a overview of what you see when you're playing. That's your little player, and yeah, you get a fairly wide area of what's around you. These are your villagers. You can command them to follow you, wait, or just run. If you tell them to run, they try and head towards the exit as best they know. These are the bad guys. There's the orcs that run around and the boss. Next, and then there's little game features. There's pickups, armor, health, and a weapon. And that's basically the map. It's pretty much a big maze. And there's obstacles within each area. So each separate room, doorways, and then stuff to navigate around within each room as well. It's just a top-down-ish overview. And some video of what it looks like just to run around within the map. There's your little villager. Eventually we'll tell him to follow us. Yeah, so every time we drop the dagger on the screen, the villager will follow. The little glowing thing is pretty much the only clue you have towards where the exit is. So you really do have to hunt through the map. And the game doesn't end unless either all the villagers are dead or until you rescue whatever is alive. Now we'll go on to machine learning. Just a quick summary of what we actually tried to do was some Q-learning with a neural network to estimate future rewards for whatever actions. So basically we tried to replace the player with an AI that would learn to win the game as it played. The actual, though the objective is fairly simple, the amount of things you can do can get complicated, so we just focused on an intelligent thing that'll learn to navigate towards the exit, though it doesn't know where the exit is, and would just drop markers on his way to guide his villagers.
So we use a system called Q-learning, which tries to predict how much reward it can get based on where it is, and so the features it has access to, and also the actions. So you feed it what possible actions it has, and it will give you a Q value, and that Q value attempts to maximize long-term rewards. So here's a system that is early in learning. So the system started here and has done a couple of trial runs. So to begin with, it's all 0 in anywhere it has not been. And here it would have had a policy to move along here. You can see some scores where it eventually got to the goal at the end. And so that has rewarded this action here to move to the goal square. And that reward slowly filters back to previous squares. So with more runs, you can see the reward slowly ticking over to each square. And here we can see after lots and lots of runs, these actions in a particular state will slowly converge. And so the interesting things are this particular iteration, it's kind of scared to go next to the danger area. It thinks it might fall in, so it actually wants to go on the longer path here. So this action would have been in the random. So because the policy is random,
you can get some funny features like this where the actor would have moved up to here, moved back down, and then died. And so it thinks that moving up here is kind of dangerous, just because of random evaluation can lead to things like that. And so with a grid system like that, on a big maze that we had, we wanted something that could estimate those Q values in a sense without having that huge lookup table and letting values slowly filter around, which would take a long time and not be very practical in a dynamic setting. We wanted to use a neural network to estimate those feature rewards, which Andrew can talk about.
Yeah, so like Jeremy said, the grid-based system doesn't allow for any sort of continuous inputs. So we thought that a neural network would be a good option to replace the Q valuation. So essentially we're trying to create a function approximator to replace that function. So with it, from any given state, we can give it a set of features, say its position or how many enemies are close by or whatever it might be, and then we can evaluate the Q values for each of those, for each of the actions we could take. So, and then we can pick the best one, and then that is the best action to take. So some of the inputs we experimented with were distances to the goal, distances to walls that we knew were there, and relative offset to the goal based on the direction we were facing. So if it was, the goal might have been, so many units to our right and so many units forward. And the actions that we could take that we tried were movements up, down, left, right, also steering mechanisms. So you could either turn left, turn right, or move forward. So the output for the neural network was a single value that represents the Q value for that combination of features and action. We did toy with having multiple outputs as well. So instead of being just the single Q value for that action, it'll output the Q values for all actions, and then that way the network will run once and that gives you the options rather than having to run it multiple times. So our implementation in Unity involves creating a neural network with random weights. Then we would go into a cycle where we would explore randomly based on an epsilon greedy algorithm. So we would either pick the best action or it wouldn't, based on a probability that would decrease over time. So we'd explore, we'd calculate Q values, then after taking action, we'd train the network, decrease randomness, and then start over again and do that multiple times. And then eventually we'd turn off the learning completely and see how the agent would perform. So yeah, we tried a few different things. We tried online learning in that it would update after each action. We also tried some offline learning in the form that it would take a bunch of actions, so say 100 steps, and then work backwards through based on the reinforcement that it got. So we had different rewards as well. So based on the distance to a goal, range, yeah, so we had different ways of updating the Q values as well, so they're simpler formulas. So we tried using them and then more advanced ones to see if it helped at all, which it didn't make a massive difference from what we could see.
So essentially, what we ended up with was something that did not work very well. It would learn sort of one action and decide, well, we would get the Q value for actions, and using a small time step didn't help. it was the neural network was just being flooded with too much of the more recent information, and we needed a way to get it to remember and to relearn previous histories. And so we have a quick video of it learning sort of just one action, and it.
So the goal's at the end here, and
yes. So we're trying to get to this point here and not run into walls. If we run into walls, it dies, and an update for the neural network backprop will happen. So the main problem is differentiating between the actions. It's difficult to get a nice balance between learning what the rewards will be and not just choosing the last thing it saw and just blindly running towards the last action.
Yeah, so modeling in short time steps was not a good idea, as it didn't know essentially what it did before to get to that point, and it just think, all right, well, that was the least negative I did, so I'll just keep running into this wall. And yeah, so instead of modeling each step, we should have probably done room by room instead of just small movements, and maybe adding some sub-goals along the way to reward it to the final goal, because at the moment it's sort of only getting rewarded for reaching the end. And yeah, sort of finding a way of reteaching its history as well would be a good idea. And that's it.
All right. Any questions? Or is everyone starving and wants to have a muffin? All right, in that case, we'll turn the group again. And we're just going to take a quick 10-minute break after the 5%. Who's team number 1? All right, okay, so we're back on. We've got 4 presentations to go. We'll start off with Nick and Loic on following Zeus and whatever other Greek god they could come up with. That's it?
Poseidon.
Poseidon? Okay, great. So, up to you guys.
Thanks.
Thank you. So, my name is Loic, this is Nick, and we work on the game Follow Zeus. So first, we'll show you a little trailer to remind you what we did on the first assignment, what are the gameplay of the game. I will talk about it too, and then Nick will talk about the machine learning and the challenges we had during the game. So, I go for the trailer. We had fun.
You had fun.
So, you are Zeus, you are a cloud floating above the map. You don't care about obstacles, you are just moving around. And you can move with a right click. When you hit space, you can kill enemy. And so this is the main attack, kill. You can also stun enemy with a lightning storm. And so above it's the your follower, you have to guide them to the temple, and this is Poseidon Zealot. You have to bring to avoid them. They are in patrol around temple and on the map, and once you get your follower, they are trying to chase you. Yeah. So.
Thanks. So, if you.
Nick, come to us.
Yeah, sorry. So if you remembered from the first presentation, the Follow Zeus game was not really much of a game, but more a tech demo. So we added a lot of 3D stuff into it, made it more of a game, where the whole point is to, you know, take these followers to temples. You score points by doing that. You even score points by not using up all your ammo. It gives the player an incentive to think about really how they're going to, you know, use these attacks. So like Loic said, there's two main attacks. There's a bolt attack and a strike attack. The bolt attack kills predators, or in this case the zealots, and a strike attack stuns them. And we'll get more into that when we talk about the machine learning. So Follow Zeus is a really basic game. It's very simple, and when it came to looking for a place to apply machine learning, that was our first challenge. We looked at all these other techniques where it came, you know, genetic algorithms, neural networks, I think reinforcement learning. There was some stuff on action prediction and I think parameter tuning, which we thought we might go that direction, but in the end we decided to throw a decision tree somewhere in the game and learn that decision tree first and then see the difference. So the two candidate places were the predators or the prey. We decided to put it in the predators, the zealots. In the original game, whenever a follower, Zeus's follower, would come up to one of these predators, they would just attack with no regards to their own safety, just, you know, 100% confidence that they would just go in and go for it. What we wanted to do was make them smart, and I use the term smart lightly here. We wanted to give them some sort of balance where they still need to attack but also want to survive the game at the end. So what we thought we'd do, and this was the whole idea, was learn from the players' attack habits, see how players play the game, learn when they use bolt attacks versus when they use stun attacks, and then knowing how players play the game, adjust or learn from that and adjust the predators or the zealots' behavior to account for that, and hopefully make them appear they were thinking about it, and or give the illusion that they were a bit more smarter than they normally were. So yeah, it was decision tree learning we decided to implement. So the way we did this was every time the player would play the game and make an attack, whether it's a bolt attack or a strike attack, we would log the data, and we identified certain attributes that we wanted to track to sort of get a feel for when players make strike attacks versus bolt attacks. So some things we were tracking were things like how much bolt attack ammo does the player have, strike ammo, are followers currently following the player, have they saved more than half, have they lost more than half. We thought maybe some of these things would come into like a psychological decision on a player on when they would use some attacks or not use some attacks, because the attacks are limited. You only get a certain number of attacks. You can't kill every predator on the map, so you have to, you know, balance that out and use them wisely, I guess. So we sourced data. We got training data. We'll talk about that as a challenge later in terms of it was difficult to actually get this training data, but ultimately we used this algorithm that was in Millington in our textbook for the subject on analyzing the attributes that we were observing and basically obtaining the information gain for some of these attributes. And a couple of things came out when we completed our analysis. We saw that the information gain for all the attributes we were tracking were very low, one, and they were all very similar. So to me that suggested that there was no one overwhelming attribute or observation that really gave us an idea of, with massive confidence, that that's when a player would use a certain type of attack versus another type of attack. There was a slight difference. Has followers, meaning the player is being followed currently by the prey or by his followers. We found that was one of the higher information game attributes. So that kind of, knowing that gives us an idea that maybe the player will use a bolt attack. But ultimately what we do with this now is we create a decision tree on how the player attacks. So has followers, you can see that the player uses a strike attack when you follow the left side of the tree, but when these three attributes are kind of satisfied, then it's more likely they'll use a bolt attack. which a bolt attack can kill a zealot. So the idea here was use this tree, reverse it in a sense, where now the prey, or the zealots, in this case, can use this to determine when they should attack. The idea being, if we find that under conditions A and B, the player is more likely to do a bolt attack, maybe the zealot should not attack prey at that time and antagonize the player, and maybe, you know, have a better chance of survival. So when we flip that around, we attack with high probabilities where the player would normally strike, which is a stun attack, which won't kill a zealot. And when he or she would normally bolt attack, we would attack with a low probability. We wouldn't attack with no probability at all, because then you just have these zealots hanging around not actually doing anything. So it was just more a probability thing for us. And so we implemented this tree back into the zealot state machine, and the results, when some of these conditions are met, the game feels different. The zealots would not attack all the time. Whether it was a successful application of machine learning, you know, that's debatable. But the game feel did change. We don't have any metrics to show that because it's just a very, very simple application. But there was a difference in the gameplay. So yeah, like I said, the zealots are caution at certain times, and that's basically times when usually you can notice it when the player has followers following him, and most of the prey have already been lost. So balance was difficult. You know, even introducing some probabilities, it still didn't feel natural that sometimes these zealots wouldn't attack. I mean, it just felt like, well, you know, if you have people following, they should just attack. So it was trying to strike a balance between this machine learning and making the game interesting and playable. That proved to be a bit of a problem. The game was simple right at the start, so it was really difficult to find a place to apply the machine learning. And not only that, we didn't have many attributes that we could really track, or observations we can make when we were tracking against the actions of bolt attack, stun attack. So ultimately the results were a little predictable. We had a feeling that's the way they would come about. So you could argue, well, we could have just created that decision tree in the first place, and maybe we would have seen the same thing. But the point is, we learned that tree from having players play the game, not by what we thought the players would do. So, you know, the argument can be made that you still go through a machine learning process. It's just that it was such a simple game that we didn't learn anything we probably didn't think was going to come up in the first place. And we were a little bit on the back foot just because we were trying to catch up from the first assignment, where it was more a tech demo than an actual game. Like Sean said many times, data gathering is difficult, and if we learn anything from this, don't leave data gathering to the last minute.
I said that to you.
Yeah, you did, but we waited for the last minute for that to sink in. So, you know, we didn't get as many players playing it as we wanted. We did do a lot of runs. Even when we were playing, we tried to play as different players, but that doesn't work. You need to get people, you need to get a good sort of cross-section of the player base to play it and to really see what players in general will do. Data analysis was a manual process for us too. We didn't have a fully automated framework. We were automating the logging, but the actual analysis, because we just did it through one pass, we got our training data, we analyzed it, and then we applied it back into the game. It was just one pass through it, so we just analyzed the data manually, semi-automatic, I guess, with spreadsheets and whatnot. Ultimately, we would have liked to create a more automated framework, I think like the Overlord game had, where they sort of automated a lot of their data gathering and analysis and that kind of stuff. But ultimately, you know, whether was it a successful implementation? Yes. Was it a successful application? You know, probably not. Did it make the game any more interesting? We're not really sure. And we'll probably say no, but regardless, we went through the process of identifying attributes, identifying observations, finding a place for machine learning, in this case decision tree learning, and then, you know, going through that analysis process, finding out how difficult it is to source data and actually get good data, not fudging the results, and, you know, putting them back into the game, and just to see if it felt, looked, different. So it was definitely a worthwhile process regardless. Cool. Thank you.
All right. Questions? No? Any online questions?
No.
No? All right, cool. Let's thank these guys. And his team. All right.
Yeah. We're Group 6. We're going to go through our project. Austin's going to start off, give a bit of a recap on our game and talk about some of the improvements we've made to do the machine learning. I'll walk through what we did for our machine learning, and then Sam will talk us through the training that we did. I'll hand it over to Oscar.
So just to recap what our game's about. It's polar bears and penguins. The human player, at least in the original version, is herding the penguins toward these safe zones in the corners of the screen. The polar bears are chasing them around, trying to eat them. So we made quite a number of changes to the structure of the game for the machine learning version. We added infinitely spawning penguins. There's now 5 polar bears per run of the game. The penguins can fight back. They can actually throw snowballs at the polar bears. And the polar bears have health. And they can heal themselves by running to a hospital point. So the idea of these changes is so that in the original version of the game, basically there would be just one thing that the bears would do, which was eat the penguins. They would have no reason to do anything else. So we've added all these different situations so that there'll be a reason for the polar bears to have to think about what they're going to do. So, for example, if the time's running out and they're on low health, they might decide they might just want to eat a penguin, whereas if there's plenty of time left, they might not want to eat a penguin, they'll just run to the hospital instead. So we wanted to create basically a reason to make different decisions. Next slide. So we ripped out the finite state machine, and because basically it's superseded by the neural network. And these are the different actions and inputs that we applied. So we just reworked the logic of the polar bear and made it consult the neural network whenever there's a change in the situation of the game. So for example, when it's eaten a penguin, or when it sees a bunch of penguins, or when it reaches a destination. And then just basically gave it a reward when it eats a penguin and gets punished when it dies. So those are the inputs.
That's me. Cool. So, as Oscar mentioned, we used a neural network for the AI of the polar bears. No one in the group had ever made a neural network, so we thought, why not? May as well. So the first thing we did was check the textbook. Next slide. I know some other groups have already gone through this, but in case you've forgotten, a neural network works like this. You get some inputs, which are these nodes here. It goes through some hidden layers, and then you have an output down the end. You can have multiple outputs. The inputs are the ones that Oscar mentioned before, which was the, how many penguins are nearby, are you eating a penguin, is the hospital nearby, etc. And then to train the network, the textbook recommended backpropagation. So that's where you get your result and then say, well, no, I actually wanted the network to do something else, and then you go back through the network to adjust the weights. I've simplified this a bit by showing these adjustments are actually the weights, not the perceptrons themselves. So this is all great, and we actually built this. We spent about 3 or 4 weeks working on this system, and then we realised, well, how are we going to train the polar bears with training data? We thought about generating the training data, but we're looking at tens of thousand units of data, and we thought this doesn't seem right. So back to the textbook. And then I found this paragraph of the intro, which I missed the very first time I read it, telling us that the author had never actually used backpropagation in a game before, and we'd spent all this time building it. It was kind of obvious because we found mistakes in the code he provided, and I wrote to the author of the book and said, I think this is wrong. And he goes, yeah, I'll check my code over and update the errata because it was wrong. So anyway, luckily Justin gave us some good advice, and that was to try genetic programming, neural network. So that's where we take the neural network that we built and then convert the weights into a genome. Basically, it's pretty straightforward, just grab the values and they come down into this sequence. Once we had the genome, if we can get this slide, we can cross them over with other neural networks. Again, like another group mentioned, you don't want to split the network in half, you just want to grab it on the weight points. and then you can create offspring. We use 2-point crossover in our implementation, which is pretty much just crossover once. Next slide. And then we applied mutation. We tried a few different mutation methods, but in the end we just went with like just randomly varying one of the weights. But we tried exchange mutation, etc. And for fitness and selection, we did tournament selection, which I think if you will come up next, where basically you grab 2 genomes, you run them through to get their fitness, and then there's kind of like it's like a battle, and the winner of that becomes parent A, and then you do it again, and you get parent B. We didn't want the solution to converge too quickly. It's a global search, so we wanted it to, to try and keep the offspring with not always go for the best values. But with that said, I did do a version with elitism, which kind of improved results. That's where you always advance the best solution. But it was a lot of fun, but we'll hand over to Sam to walk us through how we trained the network.
Yeah, so the game had to run a whole bunch of times for each genome and per population, so we wrote an autoplayer that would sort of approximate the behavior of a player playing the game. Basically, it just moves from spawn point to spawn point, accumulating penguins until it gets enough, in this case 10, and then it chooses an exit point. It chooses an exit point that has the fewest polar bears around, or if there's none, it'll just go to the closest one. And the player's input is pretty simple. That's all they really do in the game, so that was pretty consistent. The locations of the spawners and the bears were also randomized each time the game ran, because we didn't want to sort of overfit for a specific layout of the game. But this meant that the fitness had the chance to vary somewhat, even if you had the same network that was running. And so the fitness was rewarded and penalized across all the polar bears in the network, all the polar bears in one run of the game. So they're all the same brain, they'll all be making the same decisions based on input, but they had their own independent inputs and outputs, and then they were scored cumulative. So initially it was +1 every time they ate a penguin, minus penalty 20 anytime they died, and -1 for each freed penguin that the player managed to get out. And so this is the game running at 10 times the speed. We reduced the time of the game because it's time-based. It's sort of about how many you can get done at the in a few minutes, but we reduced it to 90 seconds at 10 times, so it took about 10 seconds to run a game. And initially they were just, there was no initial data, so on the first generations they were just doing things like running all the way to the hospital even when they had full health and just sitting there for the whole game. Like they were just completely random, but then after a few generations, those was quickly bred out. And so the first lot of results created these polar bears that did kind of what you'd expect. They were initially aggressive. They'd move towards the player when they didn't have any penguins in sight, because that's where the penguins always go towards. They go towards the player, and they would eat them when there was one nearby. But it did learn that once its health drops a bit, or when it's sort of outnumbered, his health at the moment is 56 out of 100. It would just sort of run into the group of penguins and do nothing, and just move towards the player, just kind of bother, which was actually a useful thing because it disperses the penguins and it makes it difficult to get to the end. But it was interesting that it learned that. Unfortunately, the polar bears don't have any inputs knowledge about each other, so even if they did outnumber the penguins and had quite a lot of health, because they're all independently minded, they would all sort of just run together and do nothing as a group. So in our second results, we were trying to mitigate that. So we, first of all, increased the fitness reward for eating penguins. We wanted to encourage them to eat more penguins. And then we created a new input so they would know the number of other polar bears nearby with this sort of intended effect, with the desired behavior of hopefully learning to coordinate attacks. And we fixed a few bugs that were happening, that they were getting stuck. And then we increased the topology network to sort of allow for that extra learning with that extra input. But the results weren't great. They sort of just were overly aggressive, and these polar bears in the second run of training just always ate, always tried to eat, always tried to grab it, even if they had low health. And you can see this, they just are getting pummeled. And this time they did kind of learn to go to the hospital. See, this bear is going to the hospital, but it seemed rather arbitrary. He had 64 hit points. He probably didn't need to do that, whereas these other ones that have lower, they're still trying to fight. So that one didn't work so well. So we tried another lot, this time increasing the game time that it was running from 90 seconds to 2 minutes. Obviously, we would like to run heaps, but we had a limited amount of time. So that was with the idea that hopefully, with the desired effect, that it would learn some, I'll just go forward a couple, some foresight to be able to have the time to learn to go to the hospital and come back. And then we increased the damage, but these results were similarly arbitrary. They sometimes attacked and sometimes didn't. And it's difficult due to the opacity of the neural network. You can't just sort of read the string of floats. It's not parsable to a human exactly why it's deciding to do things, and you can sort of play around and test it. But due to the chaotic nature of the game, it's sort of, some of them are attacking, sometimes they're not. So even this bigger input and these tweaks were still not ideal. They didn't seem to be behaving entirely intelligently. So it turned out that the initial training was the most interesting one at the best results. And as for a theory for why they were overly aggressive, was perhaps because it did learn that was optimal, because the autoplayer was sort of always run to the exit, and when I was playing the game then in those videos, I wasn't behaving the exact same way. I was sort of gathering an army and trying to fight to see how it would react. It possibly just learned that when the player runs to the exit, it is in its interest to sort of die near the exit, because the penguins don't actually know the difference between a live polar bear and a dead polar bear. It would still avoid. So if they die near the entrance, it just blocks the penguins from getting out. So, it's possible that might have been why. But overall, it was sound tech. It did sort of improve from our scripted version a bit. It couldn't quite handle those more complicated tactics, but that perhaps was just an issue of tweaking variables, and maybe with more training, with more tweaking the mutation factors of the network size and the populations, we might be able to get there.
So just to finish off, genetic programming worked out great for us. Even though it wasn't perfect, it was really, really interesting to play around with. Neural networks are hard to debug. Many times we had to step through the code to try and work out what was happening and why things weren't working out as they should have. And like we said in our last presentation, polar bears and polar bears don't live together. So, any questions?
I think I missed this at the start, or maybe the previous presentation. How were you attacking the polar bears? Was it the player, or was it the penguins?
The penguins. So,
yeah, the penguins would autonomously attack any time a polar bear basically had a penguin in its mouth. So if the polar bear attacked, anyone in the vicinity would attack back, which is sort of why that bothering behavior was like, the penguins weren't attacking back because the polar bear was not actually doing anything. So yeah, it was autonomous and reactionary.
We thought it would be fair that the penguins helped their friends, but otherwise they just ran away.
What was the total population size? Like, do you have some multiple batches?
Yeah.
The question was what the population size was.
Yeah, we did multiple trials. I found when I was early testing that a larger population worked a lot better because it added a lot more diversity at the start. When we did the training, we did around 30 population. We had 70% crossover and 30% mutation. I would have liked to have gone larger than that, but training took hours. Literally hours.
And there were about 50 generations. 50 for the first time. I think we pushed up to 60 the second time. But again, it was like 7 to 12 hours of running this to get to the end of it.
So basically sped it up 10 times and just left it overnight running and see what happened.
Tournament selection, you selected 2 people and they battled. I was wondering if you guys tried doing it with a greater number of people, because I remember when I was doing it, I chose half the population and improved it substantially. Because when I just used 2, it was like sometimes all the bad ones were making it to the next generation.
I probably didn't explain that very well. Population was 30, so when we selected a new population, we'd randomly grab 2 out of the previous generation, check their fitnesses, and then the better one would become pair 8, and then we do that 30 times. And so it was randomly selected across the whole population 30 times until we had enough population to keep going. Why we chose tournament selection was, I heard someone talk about it last semester, and they said it was really, really great way of doing it, so yeah.
And no reason?
Yeah, it was a lecturer, so I assumed they knew what they're talking about.
All right, cool. Thanks, guys.
Okay, so hi everyone, this is Isaac, I'm Lucas, and we're going to present our game, which is named Traps. So here is what we're going to talk about today. First, an introduction of the game, and just after the game concept, and after talking about the machine learning system, and what we experienced, so the troubles and the difficulties, and to finish the resources we used. So the goal of the game is to make a game with a machine learning system, and compared to the first assignment, we changed a lot of our game concept because it was not it didn't fit the goal of the second assignment. So the first assignment, our first assignment was a game about wolves and hunters. So we were leading wolves, trying to escape hunters, and we had to go to a point to make some scores. So the new game concept is more like a tower defense game. So you have a base, the red rectangle on the right. You have to protect it from enemies coming and attacking the base. And so how do you protect it? You protect it by putting traps on the map. You have waves. You have waves. Enemies are coming in waves, so you have a certain amount of enemies in a wave, and each time a wave is over, another one is coming with more enemies, and if you survive the waves, you're getting the score.
Yep, so what our machine learning methods we used was the neural network AI along to do the inputs and outputs, and then also use the we use the sigmoid function as our activation function. And we also try to use attempts on like just a basic single layer perceptron neural network, but it kind of gave us a pretty funky result, which we did not like. So then we just switched it to a more multi-layer method towards the end, and then with using genetic algorithm to adjust the weights along the way. So the following video is going to show a bit about the game itself, and show it from YouTube itself. So I'm going to skip ahead a bit because I may have messed up the recording a bit. So yeah, you got some like weird result, like where the AI will just keep on going into one certain direction, keep on hitting itself in the head in the wall every time. But there were some points where it would like actually go towards the base once. But however, I think the fitness function, either the fitness function or something else went wrong during the process, input process. So yeah, our current AI state has lots of flaws and bugs right now, so can't really demonstrate it properly at this point. But so with our genetic algorithm, it's pretty much been explained through the previous presentation, but I'll go through some of the methods that we use to to help mutate our chromosomes. So first we use the roulette wheel method to select our individual chromosomes, so the one with the best probability by this fitness sum. So its fitness divided by the total amount fitness will be its probability, and then we go through a random number, and if it lands that random number, it would select that as the parent at that point, and then we just use the crossover point method to help create our two child chromosomes in the end. And that was by just picking one random point. And so here's our decoding structure on the machine learning. So we first create our neural network, and then and then get the chromosome to, and then and then our chromosomes has its own weights, and that network is going to grab the weights from that population of chromosomes, and then it just starts beginning training and learning, get all the data it needs, and then it starts to evaluate the fitness and say, okay, did any of these guys reach to the targets? If not, then stop the training. If it did, then stop the training. If it not, go through a new generation using by going through the selection, crossover, mutate, and then create a new generation towards the end. So the troubles and difficulty was that it was a bit hard to try. Like it's easy to understand the concept, but it was hard to code the genetic algorithms and neural networks and try to debug everything. And there was some issues where the AI would just try to go back to the previous generation rather than continuously make new generations and try to evolve along the way. And it was pretty hard to try to teach the AI to go from one point into another. And so yeah. And these are our current resources, so we just used Unity 3D, and then we followed the book that was suggested, which was the AI techniques for games and programming. And also I grabbed some notes, genetic algorithm notes, to help me understand the methods and what to do along the way, and some neural network explanations from AI Junkie to help. So yeah, any questions?
All right, any questions for these guys? No? All right, let's thank last two. Thanks, guys. Rightio, let me bring the lights back on. So that, no, just turn the lights off. All right, so that concludes all the presentations for the day. Given that one group didn't present, let's take this time. If you have more questions to ask each other, any questions from each other from previous presentations? Yeah, Nick?
A general question, just because I'm pretty naive when it comes to neural networks and genetic algorithms.
Okay, shoot from the guys who did this
stuff.
stuff.
Could probably answer this. Is genetic algorithm something you do over neural networks? Is the term used interchangeably, or are they two separate?
No.
Two separate.
They're two separate things.
I think completely separate. Two different techniques.
So the question here was, genetic algorithms versus neural networks. A lot of them combine them. Some of you guys combine them. So the question is, do they have to go hand in hand? Are they the same thing or not? I think the answer is that they're two different techniques, right? So those that use it hand in hand or use it together, can you tell us why you use it together? I think some of you did explain it, but Michael?
So the problem is, if you use back propagation for a problem like ours, where the data's coming in continuously, so at each instant in time, the problem's being told, here's all the positions of these things, and it has to make a decision. With backprop, you need labeled data, so these are the inputs, these are the outputs, and then you train the network on whether it's going to guess correctly what to do from the inputs. But it's very hard to say, there's a snake here and there's a fly here. Where should the frog go? So it's very hard to say, here's some inputs, here's the correct output, and get it to learn that. Whereas with the genetic algorithm, you can sort of judge over a period of time. So over 2 minutes, did it perform well or did it not? And it's much easier to come up with a fitness function for that than it is to assess the behavior of each specific time. So it's going to make sense.
Yeah.
I actually found that two different approaches really interesting. They were like kind of a split between that. I was really happy with how our back propagation worked. And as we explained in our talk, we did it by having reinforcement learning so that it was checking the neural network and getting outputs on every update, but it wasn't changing the weights until a reward or a punishment happened. And so basically if something bad happened, like it got shot or it picked up a flag, then we'll say, well, your desired output of your last set of states should have been the opposite, the punishment should have been the opposite of the decisions you made.
Did you use an eligibility trace then, so the punishment or reward got propagated back?
Yeah, so it went through every single way. So basically, it wouldn't change the weights in the neural network until something good or bad happened, and then it would change the last set of...
If the decision was really bad, and the decisions leading up to it were really bad.
Yeah, exactly. Yeah, something like that. And we found that ours worked really well. We actually, originally, before we ran it into the game to test our backpropagation algorithm, we ran it on the Iris data. I don't know if anyone's done data mining, it's one that was popular in that. Basically, it's a set of training data for machine learning or data mining, where you get, there's like 4 different types of iris flowers, or 3 different types, and you get like the length of the petals, the stems, the width of each petal. And by putting in those basically figures for each of those 4 attributes, you can determine which different type of flowers it is. So we use the exact same neural network that we had using backpropagation, and we're able to predict with like 98% accuracy of which one it was. And then we used the exact same technique on our initial policies. We got about 91% was, I think, was in our slide.
Yeah.
And then we just upgraded the weights according to how the game was playing using those reinforcements.
Ruben, you want to say something?
Oh, well, yeah, it's just, it was interesting how much of a way that, how much it was that the initial, like getting it to learn the initial policies was really interesting, but then actually making sure your initial policies are like correct was just as, took just as much tweaking.
So I guess one thing, I guess what you all learned was there's no magic here, right? It looked like magic at the start of the semester, I guess, but it isn't. Right? When you actually go coding these things down and writing things down, a lot of things you got to consider, right? The lesson learned, the biggest lesson learned, as Nick said, is data collection is not easy with these things, right? Learning is great, but you got to have data to learn over, otherwise there's nothing to learn about, right? And that often is the hardest thing with these kind of things, right? So it's good. So far, I thought it was all great. So well done, everyone. I think you should all give yourselves a big round of applause. Well done. Good stuff. And that brings us to also the end of the semester, although we'll recap stuff on Thursday again just for an hour, right? Talk about exams as well. Hope you guys enjoyed the session. Hope the viewers watching enjoyed the session as well. Thanks, Robbie, for recording these things live. And what will happen is Rob's going to...